Today we're going to discuss the digestion of carbs, proteins, and fats. I will first address carbohydrates, which begin its digestive process in the mouth. The average person secretes about a liter of salivary juices a day that range in pH from 6.0 to 7.0. These secretions contain an enzyme called salivary amylase. This enzyme breaks starches down into a disaccharide called maltose. Once these smaller carbohydrates reach the stomach, the acid environment will stop the activity of the salivary amylase.
It's a wild ride. Come on, ride on the magic school bus.
Once your food enters the stomach, the process for protein digestion begins. Gastrin is released in response to food entering the stomach, specifically peptides and amino acids. This in turn stimulates the parietal cells to release hydrochloric acid, which activates pepsinogen into pepsin. Histamine is also released in the stomach in response to gastrin secretions, which stimulates the secretion of hydrochloric acid by the parietal cells. Hydrochloric acid has a pH between 0 to 0.8, but by the time it mixes with the stomach contents, it will increase to about 2.0 to 3.0, which is the optimal range for pepsin activity. Pepsin breaks down proteins into smaller peptides, but it is actually the hydrochloric acid that denatures the proteins. This allows the pepsin to easily break the amine bonds between amino acids. Pepsin only initiates the process, contributing about 10% to 20% of the total protein digestion. Once the chyme enters the small intestine, the bicarbonate-rich buffers neutralize the stomach acid. Pepsin loses its enzymatic activity at pHs above 5.0, which is why the majority of this process takes place in the duodenum with the help of enzymes secreted by the pancreas. Although the stomach has an enzyme to start protein digestion, the small intestine has multiple enzymes within its brush border for carbohydrate digestion, protein digestion, and lipid digestion. The organ that releases the most substantial digestive enzymes is the pancreas. As chyme enters the small intestine, two things must happen. First, acid must be neutralized to prevent damage to the duodenal mucosa. Second, proteins, fats, and starches must be broken down further so they can be absorbed by the body. The pancreatic enzyme for carbohydrate digestion is pancreatic amylase, which hydrolyzes starches, glycogen, and most other carbohydrates except cellulose to form disaccharides and a few trisaccharides. Trypsin and chymotrypsin are responsible for the bulk of protein digestion in the body, the products of which are amino acids and oligopeptides. At this stage, the amino acids are able to be absorbed into the bloodstream through the intestinal wall. The oligopeptides, however, must be further broken down by the brush border in the small intestine before they can be absorbed into the bloodstream. The main enzyme for fat digestion is pancreatic lipase, which hydrolyzes neutral fat into fatty acids. The activity of the enzyme, as with many others, is dependent on temperature and pH. The pancreatic enzymes would be denatured right away and lose activity if the stomach acid was not neutralized by the bicarbonate buffer.
This is the neutralization of the stomach acid. It shows the hydrochloric acid being neutralized by the sodium bicarbonate buffer. The end product of the reaction is sodium chloride and carbonic acid. The carbonic acid dissociates into a bicarbonate ion and hydrogen. The cells in the stomach produce the hydrochloric acid, and this must be neutralized by the bicarbonate buffer produced in the pancreas before it gets released into the duodenum.
The remaining hormones are secreted by intestinal glands of the small intestine, specifically the duodenum and jejunum. Secretin is secreted by the duodenum in response to acidic gastric juice emptying into the duodenum. Secretin then triggers the release of bicarbonate mucus from the pancreas to neutralize the incoming stomach acid, so it does not digest the intestinal mucosa. Cholecystokinin stimulates pancreatic enzyme secretion and gallbladder contractions so that the bile stored in the gallbladder is released into the duodenum to begin emulsifying fat. Digestion of fat begin in the small intestine where the specialized enzymes from the pancreas and bile salts from the liver play critical roles in fat digestion. Bile salts only emulsify fat, breaking them into smaller portions to increase the surface area. It is the intestinal lipase that actually digests the fat, or triglycerides, into fatty acids and monoglycerides.
This picture demonstrates the hydrolysis of the ester group in the presence of the pancreatic lipase. The triglyceride is broken down into the base form fatty acid, glycerol, and the free hydrogen ions. Once the chyme enters the small intestine, there are several enzymes found in the brush border that can further digest carbohydrates, such as maltase, lactase, and sucrase, which basically split larger sugars into smaller ones for easy absorption. Additionally, the pancreas releases large amounts of pancreatic amylase, which works like the salivary amylase and breaks down carbohydrates to the small disaccharide maltose.
The gastric mucosal barrier in the stomach protects it from acid erosion. With the help of an alkaline mucus that resists acid and enzyme erosion, tight gap junctions that prevent acid from seeping into the lamina propria, and a compact epithelial cell lining. Epithelial cells in the stomach are replaced every 3 to 6 days to ensure a strong barrier is maintained. Some damage is inevitable under these circumstances, yet the gastric mucosa normally remains its integrity even under these attacks. However, if the barrier is compromised, acid will begin to back up and diffuse into the mucosa, damaging the lining of the stomach. Although the mechanisms of disruption can vary, the end result is the same. Mucosal epithelial erosion, bleeding, gastritis, and ulceration may develop if the process remains untreated.